With just a single rotation lasting a few seconds, a giant wind turbine can generate enough electricity to power a home for 2 full days. To create that energy miracle, the Netherlands is pouring trillions of dollars into one of the most intense mechanical races in history, building super wind turbines. As of today, a network of more than 2,500 modern wind turbines is operating across both land and offshore areas of the Netherlands, directly supplying nearly 20% of the country's total electricity demand, turning this nation into one of the most advanced offshore wind power hubs in Europe. So how did they manage to manufacture and raise these gigantic machines into the sky? In today's video, join Mandarin Tech as we explore the entire process of manufacturing, constructing, and installing wind turbines, one of the boldest engineering achievements of the new energy era. Centuries ago, windmills were already in use and became a symbol of the beautiful Netherlands. Their principle was extremely simple: using a system of blades to intercept the wind flow, forcing the push of nature to transform into mechanical rotation, converting kinetic energy into mechanical energy to support production. It was not until 1887 that the greatest turning point appeared, when humans changed the destination of that rotation. In Scotland, instead of using it to grind wheat, Professor James Blythe connected the drive system directly to a generator. In the same year in Ohio, engineer Charles F. Brush immediately pushed the limits further with a massive horizontal axis machine, extracting the power of the wind to produce 12 kilowatts of electricity. That was the moment when wind officially became light. From the fragile 12 kilowatts of the 19th century, this idea has now transformed into super strong steel titans with capacities reaching up to 16 megawatts, more than 1,300 times greater than the original machine. And for these mechanical giants to stand firm against violent storms, everything had to begin with a brutal battle beneath the ground. Before a wind turbine can rise hundreds of meters into the sky, everything begins with a task that seems simple: digging a pit. Engineers must excavate to a depth of 2 to 4 meters, with a diameter that can reach up to 20 meters, large enough to accommodate the entire foundation of the turbine. Every layer of soil beneath is carefully examined for density, moisture content, and load-bearing capacity, because if the ground is not stable enough, the entire structure above may gradually tilt over time. After that, hundreds of tons of steel are installed into a dense reinforcement network, forming a strong load-bearing framework inside the foundation. At the center, a massive anchor bolt ring is positioned with nearly absolute precision. This is the only connection point linking the turbine tower to the foundation. Once the structural framework is completed, engineers proceed to the next step: pouring concrete. Hundreds of cubic meters of concrete are continuously pumped for many hours to ensure a monolithic foundation without internal weak points. The temperature, setting rate, and slump of the concrete are all strictly controlled, because any deviation could affect the long-term durability of the entire structure. When completed, this foundation can weigh more than 1,000 tons, strong enough to keep the entire turbine stable against the continuous torsional forces generated by the wind. With a design height exceeding 150 meters, transporting an entire wind turbine tower as a single piece is impossible. Therefore, the tower must be modularized. The entire tower structure is divided into prefabricated cylindrical steel sections, each section having a diameter of up to 8 meters and a weight ranging from 230 to 270 tons. To transport these steel sections weighing hundreds of tons across complex mountainous terrain, engineers must deploy heavy-haul transport vehicles equipped with dozens of independently controlled axles. The most impressive feature of these machines is that each wheel assembly can automatically lift, lower, and steer flexibly using hydraulic systems. This mechanism creates a perfectly balanced transport system, distributing the enormous weight evenly and keeping the tower modules stable, allowing them to maneuver carefully through the tightest curves to reach the construction site. At the construction site, the massive assembly process officially begins. Each tower section weighing hundreds of tons is lifted into the air one by one for installation. At this moment, engineers and workers at the site seem to hold their breath, concentrating intensely as they face the most demanding challenge: coordinate alignment. At such height, strong winds constantly threaten to turn the steel section into a giant pendulum. Yet engineers must lower it precisely onto the flange edge of the section below, with an installation tolerance measured in only a few millimeters. At the very moment the flange edges successfully engage, the construction team inside immediately intervenes, tightening hundreds of high-strength bolts to lock the structure firmly in place. This lifting, aligning, and fastening process is repeated continuously until the separate modules merge into a complete load-bearing tower, rising straight into the sky and ready for the installation of the nacelle. Towering in midair at a height far exceeding the Great Pyramid of Giza, this monumental steel structure would remain nothing more than a useless block of metal without its brain and heart: the nacelle. In essence, it is a gigantic steel unit housing the gearbox and generator, comparable in size to a house and weighing hundreds of tons. Hidden inside are the main shaft, the gearbox, the generator, and a wide array of complex sensors. Unlike the cylindrical tower structure that maintains balance naturally, lifting a mass weighing hundreds of tons with an asymmetrical center of gravity into the air presents an extremely severe physics challenge. That severity reaches its peak at the exact moment when the enormous nacelle, swaying in midair, is lowered precisely onto the yaw-bearing ring at the top of the tower. This is the critical mechanical link, the vital mechanism that allows the entire nacelle to rotate a full 360 degrees automatically in order to continuously track the wind direction. At this extreme height, every lowering operation must achieve nearly zero tolerance. Hundreds of massive anchor bolts from the tower must pass perfectly through the nacelle flange before being firmly secured by a hydraulic tensioning system. But why is the nacelle so heavy? If the outer shell could be opened, what you would see inside is an extremely sophisticated mechanical system. The turbine blades actually rotate very slowly at only about 10 to 20 revolutions per minute, a speed that is not sufficient to generate alternating current electricity. The solution lies in a massive planetary gearbox connected directly to the main shaft. Through a series of ultra-strong intermeshing gears, this gearbox performs a mechanical transformation, increasing the rotational speed from about 15 revolutions per minute to approximately 1,500 revolutions per minute. This enormous kinetic energy is then transmitted directly into the generator located behind it, where magnetic fields and copper windings perform the final task of converting rotational motion into electrical energy. However, for the entire turbine to truly operate and generate electricity, it still cannot function without the final missing component, the rotor blade system. Each blade is between 70 and more than 100 meters long, equivalent to the wingspan of a large commercial aircraft, yet weighs only several tens of tons. Their aerodynamic design makes them both lightweight and extremely sensitive to wind. And this is exactly what turns the installation process into a real challenge. There are two main assembly methods used at the construction site. The first method is installing each blade individually. A crane lifts each blade to a height of more than 100 meters, while engineers must precisely align every connection point with the rotating hub. At this height, even a light gust of wind can cause the blade to begin rotating and shift out of position. The second method is even more complex, commonly called the bunny ear method or full rotor assembly. The entire rotor, including 3 blades already attached to the hub, is assembled on the ground and then lifted simultaneously to the top of the tower. A structure more than 150 meters long now becomes a giant sail, ready to be caught by the wind at any moment. For this reason, all operations are carried out only under conditions where wind speed is nearly zero. The most difficult moment comes when the bolt holes begin to align with each other. Engineers must secure each connection point with an accuracy of only a few millimeters, while the entire structure is still suspended in midair. As soon as the final bolt is tightened, the massive machine officially completes its form and is ready to begin its very first rotation. The structure has been completed, but the turbine is still not allowed to operate. Before its first rotation, the entire system must go through an important stage: testing and calibration. Inside the nacelle, engineers begin checking each component, from the main shaft, gearbox, and braking system to the generator. Sensors are activated and the control software is test run to ensure that every signal is absolutely accurate. After that, the turbine is allowed to rotate at low speed. Every small movement is continuously monitored. Vibration levels, temperature, noise, and the stability of the entire structure. If even a single parameter exceeds its limit, the system will immediately stop. When everything meets the required standards, the final step is carried out. Grid connection. The first flow of electricity is delivered from the turbine into the transmission system, synchronizing frequency and voltage with the national power grid. This is the most important moment, when a mechanical structure officially becomes part of the energy system. From this point on, every rotation is no longer just mechanical motion, but electrical energy that powers tens of thousands of homes. However, one question remains. This machine depends on wind, but what happens if the wind exceeds its limits, for example, during a level 15 storm? To avoid being defeated by such a storm, the turbine is equipped with a harsh self-protection mechanism called survival mode. As soon as the anemometer at the top of the tower detects violent winds, the pitch-bearing system at the root of the blades is immediately activated, rotating the blades along their longitudinal axis by an angle of 90 degrees, feathering so that the blades cut through the air instead of resisting the wind. At the same time, the massive hydraulic disc braking system inside the nacelle clamps the main shaft tightly, locking the entire machine in place. At that moment, the power station becomes a silent steel tower, standing firmly against the destructive force of nature until the storm passes. Today, in a country where more than one-third of the land area lies below sea level like the Netherlands, wind turbines have become one of the most important energy pillars of the modern economy. They are gradually replacing fossil fuels, cutting millions of tons of carbon emissions every year, and reshaping the entire national power system. Around the world, a fierce arms race in clean energy is taking place. Dominating this competition overwhelmingly is China. The Asian giant is expanding at an unimaginable speed, possessing wind power capacity exceeding 560 gigawatts, accounting for nearly half of the total global capacity. The amount of wind turbine capacity that China installs in just 1 year alone is already greater than the total capacity of most other countries combined. Following in second place is the United States, with a massive wind power system reaching more than 150 gigawatts. Meanwhile, the energy landscape in Europe is also being completely reshaped by wind power, led by the industrial powerhouse Germany with more than 70 gigawatts. In particular, in pioneering countries such as Denmark, wind turbines have risen to absolute dominance by supplying nearly 60% of the country's total electricity production. Even emerging economies such as India, with more than 50 gigawatts, and Brazil with more than 34 gigawatts, are also rushing into the race, turning offshore winds and plains into new drivers of gross domestic product growth. However, this clean energy solution still has a harsh, dark side that the industry is struggling to solve. A wind turbine has an average lifespan of between 20 and 25 years, while 85% of the machine's materials, such as the steel from the tower and the copper from the generator, can be easily melted down and recycled. The massive blades themselves are an environmental challenge. Because they are manufactured from a combination of epoxy resin and high-strength fiberglass, to withstand structural loads, they are almost impossible to biodegrade and extremely expensive to crush. As a result, thousands of giant blades, after reaching the end of their service life, have been dismantled and buried beneath large areas of land, creating wind turbine graveyards. A cycle of industrial materials that humanity is still striving to solve through a fully effective recycling technology. From the massive steel foundations driven deep into the seabed of the North Sea, to the precise drivetrain systems inside the nacelle suspended high in the air, and to the blades longer than the wingspan of a commercial aircraft sweeping across the coastal skies of the Netherlands. Today's giant wind turbines are the clearest evidence of how humans have transformed a nation that has always had to struggle against nature into a power capable of harnessing energy from the force of its own winds. Although there are still challenges related to material waste, it cannot be denied that these enormous machines are working day and night to carry the mission of lighting the future of humanity. If you want to better understand how the world works and explore more useful insights about great engineering achievements, do not forget to follow Mandarin Tech